Hello, in this video we're going to talk about Henry's law. So, Henry's law deals with the solubility of a gas in a liquid, and at first glance you might think, when do we ever do that? But, well, oxygen is dissolved in water, and that's how fish get their oxygen. Carbon dioxide is dissolved in soda. And so it's really a very common thing. So, thinking about how much of this gas is going to get dissolved in a liquid leads us to Henry's law. So pressure has a very small effect on the solubility of solids or liquids into another liquid, but it has a large effect on the solubility of a gas. The more pressure of the gas above the liquid, the more of that gas gets dissolved in the liquid. That makes intuitive sense, right? You got more of it on top, you're going to have more of it in the liquid. And so that's the outcome of Henry's law, basically. The equation for dealing with Henry's law is as follows. So P, gas, on the left is the partial pressure of the gas that's on top of the solution over the solution. And if you have a pure gas on top of the solution, like pure oxygen over your water, then P gas is just the total pressure. And then this is linearly related to the molarity. So on the right, M gas is the concentration of gas that's in the solution, and that's in units of molarity. And then there's a constant there, the Henry's law constant. And so the Henry's law constant depends on temperature, which leads to the temperature-dependent solubility of gases, which we'll talk about in a few slides. And yeah, so this works best if you have a dilute solution of gases and it's not very concentrated, like many of our equations in chemistry do. And so you also need the gas to not interact with the solvent. So think about hydrochloric acid. Well, hydrochloric acid is made by taking hydrogen chloride, HCl, the gas, and dissolving it into water. The highest concentration you can get in water is 37% by mass. So that's hydrochloric acid. Now, when you dissolve the gas into water, it dissociates into H plus and Cl minus and then becomes a part of the solution. And so Henry's law doesn't work for that, right? Because it really interacts with the water. Whereas if you dissolve oxygen in water, it interacts with the water very minimally, and then Henry's law works fine. Then on the right, we have some Henry's law constant for gases in water at 25 Celsius. You can list this in either bar or atmosphere or whatever pressure units you want. So, for example, carbon dioxide has a Henry's law constant listed here. What's the molarity of carbon dioxide that's dissolved in water when the pressure of CO2 is 1.35 atmospheres over the solution? So, first step, find the right equation. Here's the equation for the Henry's law stuff. And then let's rearrange it for molarity, because that's what we're solving for. And then plug some numbers in. Here's the molarity of the gas, the molarity of the gas is equal to 1.35 atmospheres divided by 29, and you get 0.047. So 47 millimolar, or 0.047 molar carbon dioxide, is dissolved in water when the pressure above the solution is 1.35 atmospheres. Another interesting thing about Henry's law and gas solubility is that when you open a can of soda, well, the pressure of the gas above the liquid suddenly decreases. And over time, especially like the partial pressure of carbon dioxide decreases when it exchanges with the air. And so over time, the carbon dioxide dissolved in your solution will leave the solution because the pressure of carbon dioxide above the solution is much lower. And then your soda goes flat. Now, granted, in these discussion of Henry's law, we're not talking about the kinetics. We don't know how long this takes, just eventually it'll reach this solubility. All right, so another thing that I just want to point out is how temperature relates to solubility. So we're used to thinking of solubility as putting a solid into a liquid, or maybe another liquid into a liquid. And this solubility depends on temperature, fairly markedly in some cases. Generally, it increases with temperature. The hotter your water is, the more sugar you can dissolve into it overall. Again, irrespective of the kinetics, right? If you put your sugar in your iced coffee, it'll dissolve eventually, but it just takes a while. So here it's just like eventually how much will dissolve, and that depends on temperature. It's kind of hard to predict. You have to mostly just try it to find out. But gas solubility with temperature decreases with increasing temperature. So an example of this is when you're heating water on your stove, and after a little while you start to see the bubbles on the inside of your pan. Well, that's just the gas that's dissolved in your water leaving the solution and kind of bubbling out. It's not boiling yet, It's just the gas that's in the water is leaving because the temperature's increased. So that's all I have for this video. Thanks for watching.